Right, let's start. So we studied about the properties of using the matrix as a matrix having orthonormal columns as a linear transformation matrix, right? So we consider this U times X, where U contains orthonormal columns, and by the shape of it, due to the fact that if they are orthonormal to each other, and then they are linearly independent, so the matrix shape should be something like this, but not short and fat, right? Because in that case, yeah, the columns will become linearly dependent. And then we discussed about their geometric interpretation. So if you remember, so we start with this regular grid, which is written in this blue color, and then now our new basis, which is each of our columns in our U, right, in this column combination perspective, and then each of these columns are orthonormal to each other. It means their length is 1 and their angles are always 90 degrees. So basically we don't introduce any distortion in terms of their grid shape, right? So if we have this kind of grid coordinates, and then if we have maybe like this kind of system, coordinate system, and then this 1, 1 becomes this point, and their length becomes different, right? And also their angle, like between these two vectors, they have a certain angle like this. And then let's see, yeah, we will this vector is mapped into this vector, and so the angle becomes different, right? So in general, the lengths and angles become different from their original values, right? But if this kind of grid system is still having a 90 degree, and each axis or each basis vector has the length of 1, and then even if they are rotated a little bit, and also they are embedded in higher dimensional space, right? So if you remember this figure, and then we originally considered this a 3-dimensional space embedded, where the 2-dimensional this regular grid coordinate system is embedded, right, into this higher dimensional space, but within that span or their column space, and these two vector lengths, the vector lengths and the angle will become the same, right? Okay, so that was the point that we discussed last time. So when using the matrix containing orthonormal columns as a linear combination, linear transformation matrix, and then after mapping an input vector into output space, the vector lengths and the angle between the two axes will remain the same, and in general their inner product will also be the same as well, because the angle and the length are preserved, right? Okay, so that was the property about this orthonormal, the matrix having orthonormal basis vector. Okay, and then now let's think of another additional property of this matrix with the orthonormal columns from the orthogonal projection perspective. Okay, so here in this theorem 10, so we still have orthonormal set of vectors, okay, and then they work as the basis vector for a particular subspace W. Okay, so we are given a subspace W and their orthonormal basis vector set. Okay. Okay, and also in this chapter, we studied about the orthogonal projection of an arbitrary vector y onto this subspace W. So let's see. So for example, in this matrix U, and let's consider it as a U1 and U2, and consider the span of U1 comma U2. Okay, and then okay, let's consider some arbitrary vector y. Okay, and then what's the orthogonal projection of this y onto the subspace W spanned by these two orthonormal basis vector. Okay, and in this case, yep, basically y projection of y onto subspace W, which is denoted as y hat, will be basically represented as a linear combination of these two basis vectors. And what was the formula to obtain A and B? So if you guys remember, and then we consider this guy, y dot U1 and U1 dot U1, right? And also B is independently obtained in the same manner in this form. And here, in this case, what was the requirement? U1 and U2 are orthogonal basis, okay, to span our subspace W, and it means their vector length is not necessarily 1, but if their vector length is becoming 1, then this guy will become 1, right? And then let's just plug in these two values. Plug these two values into this place of an A and B. And the y hat is y dot U1. And this is actually the scalar, right? This is a scalar, and the scalar times our U1, right? And y dot U1, U2, and U2, right? So this is an orthogonal projection when our basis vectors for subspace W are orthonormal vectors, right? So in this example, if we consider this y, we just simply take the inner product between this guy and this guy and this guy and this guy, and that will work as A and B, or the linear combination coefficient, right, for our basis vectors. Okay. Okay, and then let's manipulate a little bit this expression. Okay, so in this case, let's just so this is a scalar and this is a vector, and we can freely change the order. U1 and y dot U1 plus U2 and y dot U2. So far so good, right? We just simply change the order between the scalar and the vector. And let's also change the order of the inner product here. Okay, so in this case, U1 and Y1 dot U1 dot Y plus U2 and U1 U2 Y, right? And then in this inner product representation, let's just rewrite it into matrix multiplication form, where we have U1 over here, and then this guy, this inner product is, yeah, so we still have parentheses over here, and then here U1 transpose, and y, right? And then u2 and u2 transpose and y. Yeah, this vector length should be the same, right? Okay, so this part will form the scalar, right? But when looking at this, so we have a vector, and also we have a matrix as a vector as a special case of a matrix, and also another matrix which is also a special case as a row vector, and also the column vector, right? And so now let's apply the associative law. So instead of using the blue parentheses, let's use this red parenthesis, okay? And then we have y in common in both terms, right? And then we can factor them out by using distributive law, and then we will obtain. So from here, I'll just bring this part, okay, as the first sum, okay, and then after forming the sum, we will just multiply y afterwards. Okay, so in this case, we have u1 and u1 transpose plus, and u2 and u2 transpose and y. Okay, so this is a we can it reminds us of some of the perspective of a matrix multiplication. So this is the fourth perspective of the sum of rank 1 outer product, right? So in this case, let's just form this guy into a single matrix multiplication where we have u1 and u2 as a single matrix, and u1 transpose, u2 transpose. Okay, and we have y over here, and so we can write it into this form: u1 transpose y. Does it make sense? So what was this representation? So this is this guy, y hat, orthogonal projection onto the subspace W spanned by some orthonormal column vectors, orthonormal basis vectors. In that case, we first form this U containing the orthonormal vectors, orthonormal basis vectors as our column vectors. And then once forming that matrix, and then you just simply multiply U and U transpose and any arbitrary matrix, any arbitrary vector Y, and then that representation is orthogonal projection onto subspace W spanned by these two vectors. Okay, and we can also think about this representation from a little bit different, almost the same but a slightly different perspective. So U is providing these two basis vectors as the ingredient vector from the column combination perspective. And then let's first consider this part, U1 transpose Y. And then if we apply the inner product perspective of this matrix multiplication, and then this guy and this guy is what? This guy will work as this A, right? U1 transpose Y. And also U2 transpose and Y, right? So that will work as this B. And that will work as the linear combination coefficient over here, U1 transpose Y and U2 transpose Y. Okay, so these are the two scalar values that will work as a linear combination coefficient, and also we have U1 and U2 as a matrix. And so this is a scalar again, right? And so given the matrix and some coefficient matrix C, which is composed of this coefficient is easily obtained by just the inner product between orthonormal basis, each of our orthonormal basis vector, and also an arbitrary vector y, right? So we can understand this representation in this manner. Any questions about it? So here we can see some interesting properties when considering this matrix U containing orthonormal vectors as columns, orthonormal column vectors. Okay, so in this case, U transpose, this will work as some orthogonal projection onto W. But what about this guy? U transpose. U transpose U. What was that? So if you guys remember this, okay, so in this case, U1 transpose, U2 transpose, this is U transpose, and U1 and U2, right? And so in this case, first of all, it's a 2 by 2 matrix, right? And then it is 1, 1, and 0, 0, because the inner product with the same guy, same vector will become 1, but different inner product between the different vector will become 0. So only on the diagonal part that will have the elements of 1, and off diagonal part will all become 0, because they will be inner product between different vectors that are also orthogonal to each other, right? So U transpose U is identity, and U transpose will work as orthogonal projection, or orthogonal projection matrix. Okay, any questions? And this orthogonal projection, I'm not sure if I discussed about these properties, but yeah, from this perspective, orthogonal projection represented in this manner is basically a linear transformation, right? When considering this U transpose as a single matrix A, and then A times Y, right? And from this perspective, I mean, we understand the orthogonal projection intuitively and their physical operation, right? So we just make the foot of a perpendicular, and that corresponding point on the surface or inside of our subspace. So that is orthogonal projection. But here our orthogonal projection is represented as a matrix times an input vector. So what does that mean? Orthogonal projection is a linear transformation. And what is the property of this linear transformation? So we first perform linear combination, and then perform the orthogonal projection, and that result will be the same as the case where we first perform the orthogonal projection of two individual points, and then later on we do the linear combination, and then those two results will be the same. Did I explain this already or not? So let's consider some subspace W, and then maybe some point y1, and maybe y2. Okay, and then so this is a y1 hat, and this is a y2 hat. Okay, and then let's consider some linear combination of 0.7 and 0.3. So especially this kind of linear combination is called convex combination. I mean, it's a completely out of topic, so you don't need to make a note. But yeah, in this case, basically this is a weighted average, and they are yeah, this, yeah, I mean, I'm talking about this 0.7 times y1 plus 0.3 times y2, right? So in this case, what's the corresponding point? So we have this line, and then this guy, where this is 3 and this is 7. So it's an interpolated point that has the ratio of this line segment has 3 to 7, right? Okay, so but this guy is one example of this linear combination, right? And so we first perform this linear combination, and then do the orthogonal projection. Okay, and in that case, it will be over here. And then let's consider the linear combination of this orthogonal projection output of individual vector y1 and y2. Okay, so in this case, we will also perform the same interpolation between the 2 points. And because we choose or we use these 2 vectors that are both inside of W, and their linear combination in this form will also remain inside of W, right? Because W is subspace closed under linear combinations. And then this point will be like 3 to 7. Okay? So if you imagine some some of the interpolation or linear combination outside of this W, and then we first perform the linear combination and then project it, and then that result will be the same as the linear combination of these projected outputs. Okay, so in that sense, this orthogonal projection is a linear transformation, and you can also mechanically easily prove it. Okay, so you just set y1 and y2, and then some arbitrary linear combination coefficients a and b, and so on. Okay, so okay, so I mean, it's a little bit of beyond our scope, but what if U is just the orthogonal vectors? I mean, orthogonal U is the matrix containing orthogonal column vectors, not orthonormal column vectors. In that case, what will be our projection? And can we represent it as a matrix multiplication with the input vector y? So in this case, let's think of this perspective. Okay, so in this case, so we have maybe V1 and V2 that are orthogonal to each other, but their length is not necessarily 1, right? And then let's consider this a y hat. And in this case, what will be the linear combination coefficient? So y and V1 and V1 and V1, and y and V2 and V2 and V2. So these two are just the scalar values, and they are just linear combination coefficient that we also studied, right? Right? 되게 모르는 표정이지. 잘 모르겠어요? 외국 학생이 한 명도 없나 지금? 외국 학생? Any foreign students? International students over here? International students? 그래서 한글로도 다 하고 싶지만 한글로 하면 내가 설명의 속도가 한 2배는 빨라지는데, 근데 또 한글은 특히 말이 빨라. 네, 또 녹화가 되고 또 학생들이 나중에 또 볼 거 생각하고 안 왔을 거라 믿고. 네. 아니 뭐 잠깐만 한국어로 설명하면 네. 하여튼 U1부터 UP까지의 이제 orthogonal 베이시스 벡터가 있을 때 뭐 이런 이제 프로젝션이 이렇게 나타내지는 거 알죠? 그래서 뭐 코사인 뭐 이렇게 해갖고 삼각형 만들어서 이렇게 했죠. 네, 그래서 하여튼 뭐 요게 이제 리니어 컨비네이션 코에피션트니까 요거를 그냥 갖고 와서 이거는 그냥 뭐 당연히 이거는 이제 U1부터 UP까지를 이렇게 해갖고 여기 이제 리니어 컨비네이션 코에피션트 이렇게 쓰면 되는데 이제 얘가 이제 이렇게 좀 복잡하게 생긴 거라 이거죠. 그죠? 네, 그걸 그냥 다시 쓴 거예요. So yeah, I just use the v's instead of u's, right? In order to differentiate this from the also normal basis vectors of u1 and u2, right? So v1 and v2 are orthogonal to each other, but not also normal to also normal, right? Okay, and then let's just first handle or take care of these guys, which we are already familiar with, v1 and v2, and this guy is v1 transpose y and v2 transpose y, right? And then we can just write it into v1 transpose and v2 transpose. And y. Okay, so in this case that's not it, right? So we need this guy, right? And so did I explain some if you remember some of the elementary matrix. So we have some matrix. And then what about the row scaling matrix? So we have three rows, and then let's consider the scaling of the first row by maybe by 2 and 3 and 4, and what will be the corresponding row scaling matrix? So in this case 2, 3, 4. So these are all zeros, right? So in this case, we apply the row combination perspective. So this guy is the linear combination coefficient that will form the first row, right? And then 2 times this guy, and 0 times this, 0 times this, right? And so if we want to do the row scaling, and then we can multiply diagonal matrix on the left, right? And similarly, let's consider the column scaling. So we have some matrix that have the 3 columns, and we want to scale this guy as maybe 2, 3, 4, okay, for the corresponding column. And in that case, similarly, we can multiply the diagonal matrix, but this time on the right, and 2, 3, 4, 0, 0, 0, and so on. And so in this case, we apply the first column combination perspective, and so this one will work as the linear combination coefficient to combine these 3 columns, right? And that result will form our first column, right? And so 2 times the first column, 3 times the second and third. Okay, so back to this example over here. We obtained this guy, right? But we want to further scale it down by these 2 values. And although these are just a column vectors, but when viewing it as a matrix, what kind of scaling are we do we perform here? We are performing the row-wise scaling, because we want to scale this row, first row and second row differently, right? And so, okay, so we made this guy to form this guy, but yeah, we can multiply some matrix, I mean some diagonal matrix over here in this place, right? And so this guy is V1 and V2, and then over here we need 2 by 2 matrix, I mean diagonal matrix, and over here V1 transpose V1 and V2 transpose V2 and 0 0, right? So this is the self inner product of V1 and V2, right? I just rewrote it into this matrix multiplication form. Okay, so in that case we have this V1 transpose, V2 transpose, and Y. 네. 그러네요. 네. Okay, so far so good, right? Okay, and then can we represent it as also some of the matrix V? So this is capital V. Okay, so in this case it is actually so I'm gonna give you the conclusion directly. So yeah, let's consider this guy, V1 transpose V1 and V2 transpose V2 and 0 0, and we saw this form earlier. What about how about representing it into this form, V2 V transpose and V? So we have V1 and V2 and V1 and V2 over here, and then diagonal matrix will be the inner product with itself and the off diagonal part, although this guy is V1 transpose V2 and V2 transpose V1, but they will become 0, right? And so okay, I'll just leave it as it is. So this guy is V2 V transpose and V. Does it make sense? Okay, so we formed this guy, but we need their reciprocal element-wise reciprocal of this original matrix. Okay, so in this case, so I just give an answer, but this guy, this part is V2 V transpose and V and inverse. Okay, so so here this is because let's think of this 3 2 0 and 3 0 3, which is diagonal matrix, and consider it's an inverse, and that is simply this guy. Okay, so if you just multiply them together, and then you can easily verify that they are forming the identity matrix. Okay, and also we can think of this guy, understand this guy from a different perspective that we discussed over here. So so given some arbitrary matrix, we multiply diagonal matrix, and multiplying the diagonal matrix on the right performs column-wise scaling, right? Column-wise scaling. So this guy will scale the first column, and this guy will scale the second column, right? Right? So like this guy. So in that manner, 2, 0 and scaled by 1/2 will become 1 0, and 0 3 is scaled by 1/3, and then they will become 0, 1, and thus they are the inverse matrix of each other. Okay, and so if we form this guy as a V transpose V, and then their inverse matrix is just an element-wise reciprocals. Okay, so altogether, if we used orthogonal matrix, and then what will be our orthogonal projection matrix? So we have V over here, right? And then this is not an inner product, and V transpose V inverse over here, and what is this guy? This guy is V transpose and Y. So it's really a lot of V's, right? 4 V's, but at the far left and the far right, we have V and V transpose respectively, and in the middle, and in order to handle this scaling factor of these guys, V1 transpose V1 and V2 transpose and V2, that works as a denominator, and that can be formed, that can be represented as this V transpose V and its inverse, which actually is a diagonal scaling. I mean, the reciprocals of this, the norm squared of each of V1 and V2. Okay. So this is the linear transformation matrix. I mean the orthogonal transformation matrix, and altogether, if we consider it as a matrix A, and then this is still a linear transformation. Okay. And in the next chapter, this representation is actually works as orthogonal projection when we have non-orthogonal basis. So up to this point, we consider the orthogonal basis or orthonormal basis. So as a basis vector for a given subspace W, we assume that we have orthonormal or orthogonal basis vectors. But what if we have some non-orthogonal basis vector? Or for example, 1, 2, 3, and 2, 3, 4. They are certainly not orthogonal to each other, but we can think of their span and the corresponding subspace W. And still, that will be some plane that has the actual dimension as 2, right? And then let's think of some arbitrary vector Y as maybe 3, 4, 5. And I'm not sure if it's inside of W or not, but let's just consider it, generally as the vector outside of W. And then what's the orthogonal projection of this Y onto subspace W, spanned by the two just linearly independent vectors. Okay, they are not orthogonal to each other. So in this case, the orthogonal projection is represented as so let's consider this A as 1, 2, 3, 2, 3, 4, containing the columns as basis vectors, and A and A transpose, and A, you remember this representation, right? So A transpose A inverse and Y. Okay, so this is actually orthogonal projection of Y onto the subspace spanned by some linearly independent vectors. Okay, so here what's the difficult part, or what's the actual difference from this representation? I mean, the representation itself is the same. I mean, we will prove this guy in the next chapter, And so that is closely related to really important part called least squares. But yeah, here they share the same representation or same formula for orthogonal projection, whether our basis vectors are orthogonal or just linearly independent. Okay, so the representation is the same, but here if you try to compute this orthogonal projection, and then the main kind of hurdle over here is, or main part which is computationally intensive is this guy. Okay, so A transpose A. What is A transpose A? 1, 2, 3, 2, 3, 4, and 1, 2, 3, 2, 3, 4. And then you can think of, you can consider this a 2 by 2 matrix, right? So that is no longer be diagonal matrix, and thus their inverse matrix is not easily obtained. So in the case of 2 by 2 matrix, we can easily compute the inverse matrix by using the formula of AD minus BC, 1 over AD minus BC, DA minus B minus C, right? But if it is a 3 by 3 or even larger matrix, and then we have to just perform the Gaussian elimination to obtain the inverse matrix, right? So like 1, 2, 3, 2, 3, 4, and maybe 4, 5, and then we have another matrix, another column vector. Okay, in this case, so they are just linearly independent, and then if we compute this A transpose A, and then A transpose A will be 3 by 3 matrix, and then we need this inverse, and then we have to perform this. We form augmented matrix and then do the Gaussian elimination. That's how we compute or obtain the inverse matrix, right? So although the formula is the same, but this part, the inverse part, will be much more computationally intensive. But in the case of orthogonal matrix or orthogonal basis vectors, this part is easily computed, because we just perform this. We just compute V2 and V transpose V, which will have only the non-zero only at the diagonal elements, right? And they are simply the norm of each basis vector, right? And then we just take the reciprocal, right? 1 over this value, and then that's it. That's it for computing this guy, V transpose V inverse. So in that respect, computing this inverse matrix of V transpose V is a much simpler and computationally cheaper than this general case of having linearly independent basis vectors when performing this orthogonal projection. Okay. Any questions? 이해가죠? 네. 학기 후반이 될수록 항상 학생들이 포카페이스가 되고 속을 읽을 수가 없어요. Right? So that's it. For this chapter, U transpose Y is orthogonal projection when we have also normal basis vectors. Okay, that's it for this chapter 6.3, and then let's move to chapter 6.4. And this is really fun chapter, I feel. But it's a little bit, their notations are a little bit dirty, and notation looks a little bit complicated at a glance. But if you understand their intuitive process, and then you don't actually need to memorize at all about this operation that we will study, which is called this Gram-Schmidt's process. So let me first give an intuitive explanation of this Gram-Schmidt's process. So the goal of this Gram-Schmidt's process is, so initially we are given some of the linearly independent vectors, okay? And in the previous case of having also normal basis vectors and orthogonal basis vectors and also linearly independent basis vectors. And then we kind of studied that also normal basis vectors are the most, the easiest case to handle, right? And linearly independent basis vectors are the most difficult case, right? And so suppose we are initially given just linearly independent basis vectors, and can we obtain orthogonal or also normal basis vectors that spans the exact same subspace spanned by the original linearly independent vectors? Okay, so that is the task that we want to achieve over here. Okay, so over here these two are, let's consider the span of these two, and then they are not orthogonal to each other. If we compute their inner product, and then the inner product will not be zero. So in this case, how can we obtain the orthogonal basis vector v1 and v2 that spans the same subspace W, or even further, also normal basis vectors? Okay, so that's what we want to achieve over here. So in this case, let's think of this first vector as 3, 6, 0, and the second vector 1, 2, 2 is something like this. Yeah, v2 x2 is 1, 2, 2. Okay, and here we will basically perform orthogonal decomposition. Okay, orthogonal decomposition of y2 onto the subspace spanned by x1. Okay, so here this is the process. So suppose we have x1 and x2 and x3 as just a linearly independent vectors. Okay, and then how we obtain orthogonal basis vector is as follows. We just consider x1 as it is. We just bring this x1 as it is, and then when bring this x2, and then what is their angle? Their angle is not necessarily 90 degrees, right? They are just linearly independent, right? So in this case, we just change this x1, or this, we just represent x2 as an orthogonal decomposition, where x2 hat is inside of, or W1, where W1 is spanned by the previous vector x1. Okay, so it's quite similar to checking the linear independence or not given a particular vector set. So we add one vector at a time, right? And then we check whether the current vector is inside of the span of the previous vectors, right? So if it's outside, and then up to that point they are linearly independent, but if it turns out to be inside of the span of the previous vectors, and then that's when they are linearly dependent, right? So we follow that kind of a sequential process of considering one vector at a time. Okay, so here in this case we consider this x2 as the orthogonal projection, where this orthogonal decomposition, where the first component is belonging to this guy, which is an orthogonal projection onto this W1, and then maybe some z. Okay, and then we just add z over here instead of x2. Okay, so let's consider this span of these two vectors and check whether span of x1 and x2 are the same as span of x1 and z2. Will it be the same? Okay, so so x2 over here, when considering the orthogonal decomposition over here, and then it is something like this. So this guy is x2 hat, and this guy is c, right? Okay, so the span of x1 and x2, okay, spanned by these two vectors, which forms a plane, okay, and their angle is not 90 degrees. But we now consider the new set of bases that spans the same subspace spanned by x1 and x2 as like this guy, this x1 and this z2, okay. So in this case, x1 and z2 are orthogonal to each other because this z2 from the orthogonal decomposition theorem, this is belonging to w1 perpendicular, right? And so z2 is orthogonal to x1, and also their angle is 90 degrees as well. And here the question is, okay, so we obtained the z2 from as the remainder, or this orthogonal complement, right, of this x2, okay, with respect to this subspace, right? And then will these two, the span of these two different versions of the vectors are the same or not? Okay, so here in this representation, let's just rewrite it into this form. z2 as x2 minus x2 hat, right? Okay, and then this guy is belonging to, again, this guy is belonging to this guy, w1, right? And so x2 is a linear combination of x1 because it belongs to the span of x1, right? And then, so at a high level, this representation is a linear combination of x2 and x1, which is the previous vector that we had, right? And so z2 is represented as a linear combination of the previous vectors of x1 and the current vector of an x2, right? And so z2 is belonging to the span of x1 and x2, right? And then this z2 is orthogonal, orthogonal to x1, or as I mentioned, orthogonality is a more strict condition than the linear independence, right? So we found the two orthogonal vectors of x1 and z2, right? And so we found the two linearly independent vectors from the subspace spanned by x1 and x2, which has the dimension as 2, right? So it is spanned by the two vectors of an x1, x2. Originally, they are linearly independent, just linearly independent, right? And we can see that their dimension is 2, right? And then now, instead of using x1 and x2, we use x1 and z1, and x1 and z2 by changing x2 into z2, and this z2 is still belonging to span of x1 and x2, and this z2 is linearly independent, or even more strictly, it is orthogonal to x1, right? So we basically found two number of linearly independent vectors from our subspace, and thus they will span the subspace spanned by x1 and x2. So what's the theorem of it? It is called the basis theorem. What was the basis theorem? So the basis theorem is, so we are given a subspace, and we know the subspace dimension is 2, okay, for example. And then suppose we found 2 linearly independent vectors from that subspace, I mean inside of this subspace, and then they will fully span the given subspace, right? So basically the basis vectors have to satisfy the 2 conditions. The first one is fully spanning the given subspace, and the second condition is linearly independent, which means there is no redundancies at all, right? And so here basis theorem says, given a subspace that has a particular dimension, for example, for a given subspace that has the dimension of 2, and then if we found the 2 linearly independent vectors, and then that will automatically satisfy the first condition of the basis vector of fully spanning the subspace. And at the same time, if we found the 2 vectors that fully spans the subspace, and then in that case they should be linearly independent all the time, which means among these 2 vectors we should not allow any redundancies, which means they are linearly independent. And in that case, okay, so I mean if we allow the redundancies, and then it cannot fully span the given subspace. Okay, right. Let's take the break for 10 minutes and then resume at 1:10.
이거 트랜스포즈가 아니고 직교 교신가요?
아이고, 그러네요.
잘못 적으신 거 맞죠?
네네, 맞아요. 맞아요. 네, 고마워요.
스케일이라는 패턴이 들어갔을 수 있잖아요. 유닛 패턴. 거기 맥주는 어떤 한번 떠나서 스케일이라는 개념이 들어갔어. 유닛 패턴 큰 변화는 그래서 얘가 나오는 거야. 근데 얘는 그게 아니야. 엘리멘트는 영이면은 지구 같은 거 지금 그러면 얘를 배나무 같은 거 쓰라고 했죠. 얘 말고 여기 힘이 빠지는 이런 게 근데 우리 보상을 할 때는 이게 다 아니 근데 얘는 베이스 쓰면 안 되지. 아 얘는 벡터여야지. 원래 이렇게 표현할 수 있는. 아니 그게 아니라 얘는 우리가 결국에 벡터가 나간다. 그냥 벡터 같아요. 얘가 매트리스니까 매트리스. 얘는 무조건 벡터야.
질문. 아까 올소노멀이 아니라 올소고노를 때
네.
그 얘네가 분모가 안 사라져서 1이 안 돼가지고
네.
제가 그 스케일 해주는 엘리멘터리 메이트리스가 필요해서
네.
얘가 나왔잖아요.
네.
근데
네.
아예 올소고노도 아닐 때는
네.
그 얘네가 엘리멘터리 메이트리스가 안 돼서 스케일 해주는 역할을 못 하지 않나요? 근데 여기 0이
네.
안 들어가서
네, 맞아요. 그러니까
그러면
그게-
네, 여기가 유도가 어떻게 되는지.
네네. 그러니까 이게 그걸 증명을 안 했는데 우리가 그거를 이제 다음 단원에서 우리가 증명을 할 거예요.
아 다음
저거를 우리가 이제 스페셜 케이스인 어떤 올소고널 컬럼이 베이시스가 있을 때 저거를 우리가 만들었는데
네.
아까 내가 이제 증명이 없이 그게 실제 올소고널이 아니라 리니얼리 인디펜던트한 베이시스가 주어질 때에도 그게 이제 저 식이 그대로 올소고널 프로젝션으로서 역할을 그 식이 똑같다라고 이야기를 했는데 그건 이 증명을 우리가 안 했어요.
아,
네, 그래서 그거 이제 다음 단원에서 할.
아 다음
네. Right, let's continue then. So, yeah, we saw the example where we have a linearly independent basis vectors and then change it or convert it to orthogonal basis vector that spans the exact same subspace. Okay, so in this case, yeah, so yeah, we consider this x2 and its orthogonal decomposition. So x2 is the sum of this guy plus v2. So this is a z2 that I wrote. Okay, so this part is span of x1, right? Okay, and then this works as y, and this works as a u1 and u1 and u1 and u1, right? So this is a familiar orthogonal projection formula, right? And then x2 is decomposed into this part and also this part, right? Which is orthogonal to x1. And z2 or v2 is over here obtained in this form. And so if we obtain this guy, and then and then let's verify this guy is orthogonal to x1, and of course this is orthogonal to x1, right? And so this guy and this guy, and the set of these basis vectors will span the same subspace spanned by x1 and x2. Okay, instead of using this guy, we will use this guy. Okay, 들어오세요. 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 So instead of using x1 and x2 that doesn't have 90-degree angle, okay, then there's subspace is spanned by this x1 and z2, which are now orthogonal to each other. Okay, and then let's extend this case into more general case where we have more than two vectors. And in this case the scenario is still the same. So how about x3, which is a linearly independent of x2 and x1, but not necessarily orthogonal to x1 and x2. In this case it is the same. So given x3, and then we consider it's the orthogonal projection of x3 hat, which is spanned by, which is inside of the subspace W, spanned by x1 and z1, which have orthogonal basis vector. Yeah, right, z2. Okay. So this is a v2 according to our lecture. Our slide material, and then we will obtain this z3, which is a orthogonal part, right? And then instead of using instead of using x3, we will just use z3. And then z3, by definition of its orthogonal decomposition theorem, and then this one is belonging to W perpendicular over here. So let's call this W2 and W2. And also, over here, I just made the typo over here as a transpose, but this transpose is not true or not correct. So this perpendicular is the correct one, right? W2 perpendicular. Okay. So again, in this case, this Z3 is a linear combination of x1, z2, and x3, right? And so this z3 is still, z3 is still inside of the span of the three vectors in total, x1, z2, and x3, right? So over here, it will still remain in the same subspace spanned by x1, x2, and x3, but x2 was replaced into z2. Okay, but here this z3 has a nice property of being orthogonal to x1 and z2, right? And so altogether, x1, z2, and z3, these are working as orthogonal basis vector for the subspace spanned by x1 and x2 and x3. Okay, that's how we obtain orthogonal version of basis vectors for the same subspace. Okay, so this is the process called the Gram-Schmidt orthogonalization. Any questions? Okay, then let's look at this example. So we have over here the three vectors, and then we keep the first vector as it is, and then the second vector we perform their orthogonal projection on decomposition, and this is a z2, right? And so we obtain this remainder, or this orthogonal complement part, right? Or orthogonal component. And then instead of using x2, we will use this guy. And then we now have, yeah, so, and also here, yeah, we have an optional step. So once obtaining, yeah, back to this previous simpler example, where we have these two orthogonal basis vectors. So in this case, if we remember the the basis vectors that are orthonormal to each other, and then it has a nicer properties than just the orthogonal basis vectors, right? And so what if we want to just make them into a simpler form of orthonormal basis vectors? So the process is really simple. So they have a 90-degree angle, or orthogonal to each other, right? And then in order to obtain orthonormal basis vectors, we just normalize each vector. So 3, 6, and 0. 3 squared and 6 squared. 45, right? So 3 over square root 45 and 6 over square root 45 and 0, right? So this is an orthonormal version of basis vector. And what about this guy? So this guy is simple. So we just separately normalize our orthogonal basis vectors, right? By just simply normalizing each vector to a unit vector, right? So this guy is having the same direction and also having the length of 1, right? Okay, so we can have this an optional step, and in that case, what is what does it make an easy process? So let's see. Okay, so in this case, so if we already normalized v1 and v2 transpose, v2 dash, or so there are a little bit of a notation differences, but v1 and v2 prime is just some of the orthogonal basis vectors. Okay, and then now let's make it as a u1 and u2, which are also normal basis vectors. And then when projecting x3 onto the subspace spanned by these two previous vectors, and then the orthogonal projection part will be easier to compute, because this it has some typo over here, right? So this should be v1 and this should be v2 dash. I mean, in the denominator it should have the norm of the basis vector, right? Okay, and then if we already normalized our basis vectors, and then this denominator will become 1, right? So the computation will become easier or simpler. Okay, so once obtaining this projection onto the subspace spanned by the two basis vectors or two previous vectors, and then we just obtain this remainder or orthogonal component, and then this vector will be our third orthogonal basis vector, and then we can just normalize it so that the length becomes 1. Okay. Right, so looking at this figure, so we have a v1, so this is originally maybe x1 over here, and then suppose we normalize it into v1 to just maintain the orthonormality of our basis vectors, and then so this is where is our where is x2? Okay, so I'll redraw it. Okay, so this is an x1, and then we just normalize it so that the length becomes 1, v1 for example, or u1. Okay, and then maybe this x2, and then we just decompose it into these two parts of this guy and this guy. Okay, so moving it so that it starts from the origin of the same vector, and then this guy is z2. Okay, this guy is z2, and let's just normalize it so that the length becomes 1. Okay, so this is u2, right? And then now we have some plane spanned by these two vectors, and then now we consider this x3, and then we just normalize it. Okay, so over here the angle is 90 degrees, and then okay, so this part, okay, so this part is our c3, and then we just normalize it into u3 and u1, u2, and u3. Although the figure is a little bit messy, but you can imagine this process, right? And so yeah, if we have a the subspace spanned by the 2, and then if we are given x3, and then we just perform the typical orthogonal projection or decomposition, and then this part is becoming our z3, and then we just normalize it into u3. Okay, right? So I just skip this part, and yeah. So this part is typo. Typo, and let's see. This part is also typo, and this guy should be p minus 1, right? Okay, so this is the summary of this Gram-Schmidt process, but the equation looks a little bit daunting or quite complicated, but if you understood this intuitive process, and then it will be just enough. Okay, and then now let's and then we can obtain this orthonormal basis. Then we can optionally perform this normalization of each vector to have the unit length. And then now using this Gram-Schmidt process, we can it's time to study another interesting matrix factorization of a given matrix. Okay, so that is called this QR factorization. So and then this is an exact same process of this Gram-Schmidt process. Okay, so let me just show the example over here. Let's see. It's really complicated, but let's directly use or look at this example 1 1 1 1 and 0 1 1 1 and so on. Okay, so we have these three column vectors that are linearly independent. Okay, and then we know how to perform their Gram-Schmidt process. Okay, and then suppose we obtained u1 and u2 and u3 out of x1, x2, x3, and then now let's consider the matrix multiplication, matrix product or factorization form as which are our u1, u2, and u3, and let's consider this matrix, corresponding matrix multiplied on the right of this orthonormal basis vectors. Okay, so at a high level, this x1, x2, and x3 are linearly independent vectors, and then we consider their span. Okay, and then that span, I mean the subspace of these three vectors, and the span of these u1, u2, and u3 will be the same, or same as the span of x1 and x2 and x3, right? And then now x1, 2, 3, each vector is still inside of our subspace of x1, x2, and x3. And let's call that subspace as W. Okay. And of course, yeah, obviously x1, x2, x3 will be inside of W, right? And then so this same exact same space is spanned by u1, u2, and u3, right? So the overall idea of this Gram-Schmidt process is to maintain the subspace to be the same, right? Right? And then yeah, so here let's think of this representation of x1 as, yeah, x1 is clearly, yeah, inside of W, of course. And then x1 should be, yeah, it means x1 should be able to be represented as a linear combination of u1 and u2 and u3, right? Because that is inside of subspace W. And likewise x2 and x3 should be able to be represented as a linear combination of u1, u2, and u3, right? And so at a high level, this matrix product of like this guy. So these guys are actually A, B, C, right? Because in that case, that will form our first vector, right? Okay. And then now let's try to find out. Yeah, and also what's the size of this matrix and this matrix, and u1, yeah, so it's a 4 by 3, and what is the size of this matrix? 4 by 3, and this matrix is by the way called Q, and this matrix is R in the case of QR decomposition. And what's the size of an R? 3 by 3, right? Okay. And then let's fill out this each element in our R. Okay, so let's consider the u1, u2, and u3 as also normal basis vector. And when handling the first vector, we have no previous subspace to compare or to perform the orthogonal decomposition onto, right? And so here we can simply normalize the first vector, right? So that's the first step of this orthogonal Gram-Schmidt process. And the vector length is 2, 1 squared, 1 squared, and 1 squared, 1 squared, and their sum is 4, and then square root of it is 2, right? And then this is the first u1, okay? And then here the point is, yeah, point is this guy, x1. I mean the span of x1 is span of u1, right? I mean this is true, of course, but beyond that, or in addition to that, this guy is true, and span of x1 and x2 is the same as span of u1 and u2, right? So in this case, it means x1 can be represented as the linear combination of u1, and it doesn't need any other vectors of u2 and u3, right? And so, okay, so here we can have some non-zero linear combination coefficient, but for u2 and u3, they will not need these vectors at all, right? And then what about the first vector? So u1 is obtained from just the normalizing the first vector, right? And this guy is actually x1 transpose x1, because that is the norm of vector x, right? x1, right? And then here, in this case, if we just reconstruct or rewrite x1 into the linear combination of u1 and then 2 times u1, right? And so this guy is 2, right? Right, and then let's just perform the orthogonal decomposition of an x2 onto the subspace spanned by x1. Okay, in this case, yeah, we conveniently made the previous vectors as an also normal basis vectors, right? And so x2, let's consider this orthogonal decomposition, and x2 hat is spanned by u1, right? Right, and then this guy is x2 dot u1, and that's it. Dot u1 plus c. Okay? Right? And what is this guy? Can anyone tell me? So the inner product with this guy and this guy, right? 3 over 2, right? So that is the inner product between the two vectors. Okay. Okay, so 3 over 2 and u1 plus c. So x2 is this guy, 0, 1, 1, 1, and yeah, we can obtain z by subtracting this from this, right? Then let me allow to cheat. Okay, this guy. Okay, this is our z, or orthogonal component. Okay. And then we have to normalize it further, right? To have the length of 1. Okay, so was normalizing it, and then this is the this is the vector length of this guy, right? So yeah, we just divide it by this guy, right? It's a reciprocal, square root and reciprocal, right? So u2, okay, u2 is this z2 divided by, or yeah, let me just right? 이거 아닌데. 이거 반대로 돼야 되나요? So this is z2. Yeah. Okay, I already took the reciprocal, so it should be multiplied, right? Okay, so right. Right, and then once performing this representation, and then we can obtain u2 over here, which is this guy. Okay, and so u2 is 3. Right, right, and then now let's let's try to represent the x2 as a linear combination of u1 and u2. Okay, so here, okay, so we have u2 over here, which is the normalized version of this z2. Okay, and then the z2 is represented as like square root 12 over 4 times u2, right? Because that is z2, right? Okay, and then yeah, we are done over here. x2 is u1 times this guy. Okay, so what was that? 얼마였죠 이거? This value, right? And this is the linear combination coefficient associated with the u1. And what about the z2? Z2, and once obtaining z2, and then we normalize it to have the unit length, and then z2 will be we'll have the vector length as this value, once normalizing it. Okay, and then obtaining this u2, and u2 was placed over here. Okay, then now we obtain the linear combination coefficient over here for u1, and 3 over 2, and this guy, square root, and still 0. Let me make it big over here a little bit. Okay. So this is how we form our Q and R. And so yeah, I will skip the last one. Yeah, but the process is really intuitive, and you should be able to easily understand and remember the process. And so it's a matter of computation. But here, how we form this matrix Q and R as follows. So we obtain this U1 as a first orthonormal basis vector from X1, and then we compute their linear combination coefficient. In this case, we do not care how many the remaining columns are left, right? Because we can simply fill up this part as 0, right? And then we move on to X2, and then we perform orthogonal decomposition, and then we obtain this Z2 and normalize it, and then we replace that U2 as the second column of Q, and then accordingly we can fill out the second column as a linear combination coefficient second column of an R as a linear combination coefficient. Okay. So this is how we perform this QR decomposition. Any questions? Okay. And then you can continue the computation. And probably one of this QR decomposition will be included in our exam because it's a quite important part. And then let me make it a little bit abstract and generalize it. Okay, so in general we have maybe 100-dimensional vectors. I mean 3 of these 100-dimensional vectors. Then this one is x1 and x2 and x3, and then we will obtain Q as the same size of matrix A. Right? And so 100-dimensional vector and 3 also normal basis vectors. And then also this R part is still 3 by 3, similar to the previous case, right? Okay, and then here let's consider this case where we have a short and fat matrix. So in this case we have these 4 column vectors, but are they? Is it possible that they are linearly independent? It is not possible, right? So there should be some linearly dependent vectors. But here, can we still obtain the QR decomposition? Which means, I mean, in general, QR decomposition is not defined in this matrix, I think, but we have no problem of applying Gram-Schmidt's process and also this obtaining this QR decomposition. So we have x1, x2, x3, and x4, and then we consider the span of these 4 vectors, right? And then suppose, let's consider it's echelon form, and we obtain this kind of pattern where we have the pivots in the first, second, and the fourth columns, right? Something like this, right? So in this case, it means the third vector is actually inside of the inside of the span of the x1 and x2, right? So that's why we don't see the pivots in the third column, right? Okay, so in this case, let's consider their QR decomposition. So in this case, are these 4 vectors are these 4 vectors a valid basis vector for this subspace? It is not, because x3 is linearly dependent 1, so it is basically redundant vector. So even if it is removed, and then their span or their subspace spanned by these 3 vectors will remain just as the same as this original one, right? Okay, so in this case, let's just perform the QR decomposition or the orthogonal projection anyways. So in this case, the first vector is converted into a unit vector, right? And then let's consider forming our Q and forming our R, and we will have some norm of the first vector x1, right? Similar to this value 2, right? So where is this 2 coming from? So 2 comes from the norm of x1 and x1, okay? Right? So in this case, this one will be the norm of x1. Right, and then let's just obtain the orthonormal basis vector in the place of an x2, and then this one will be u2, and then we will have some value and all 0 values, right? Okay, some non-zero value for the first 2 elements in the second column. Okay, and then what about the third one? So let's think of the third one and consider the projection of an x3 okay, and then consider z3 so this part is x3 hat. Okay, so in this case if x3 is a linearly dependent vector, and it should be already inside of the subspace spanned by x1 and x2, or u1 and u2, right? And so what is the z3 in this case? Z3 will become 0 vector, right? And so when obtaining u3, we will have to obtain some non-zero z3 and then normalize it, and that's how we obtain u3. But here it doesn't give us any non-zero vector, right? And that's obvious because that is already inside of the subspace spanned by the previous vectors, right? And so this guy is 0. Okay, so it will not give us the new non-zero vector u3, right? But still, can we is it possible to represent x3 as a linear combination of u1 and u2? Yes, it is, because that is already inside of subspace w2 spanned by u1 and u2, and so we have some non-zero coefficient over here, and maybe all zeros. Okay, and then we don't need U3, any other additional ingredient or base vectors that is used to form the linear combination. Okay, and then x4, will it give a new third also normal vectors? Yes, it is. So yeah, we perform the same thing. Instead of x3, x4 is like pros w2 x4 and plus c4, and this guy will be non-zero, and then we normalize it, and then that's how we obtain this u3, right? And then we have this guy, right? Okay, so we didn't care about how many zeros we have in the lower part, but because we have three columns, three also normal basis vectors to fully span the column space of this matrix. Okay, so we have three also normal basis vectors, right? And then our R over here is 0 and 0, 0, 0. Okay, so in this shape, it's like this kind of upper triangular matrix. So compared to the previous case, in the previous case, we will obtain non-zero and 0, 0, and non-zero, 2 non-zeros and 0, and 3 non-zeros. Right? So in this case, it's like this upper triangular form. Okay? So in the case of QR decomposition, Q will have also normal basis vectors, and R will be upper triangular matrix. But if our original matrix has some linearly dependent vectors, okay, and then the number of columns of Q will be the rank of A. Okay, what is the rank? It's the dimension of the column space of matrix A, right? So the number of columns of Q will be the rank of matrix A, and then R will be, so this is the rank, and then this guy is almost like our echelon form or upper triangular matrix. Any questions? So here, yeah, this is a, by the way, valid upper, yeah, echelon form, because we can think of the pivot over here. So the third one doesn't have any pivot. But anyways, yeah, we can kind of generalize this QR decompositions in this manner. Okay, any questions? Right, and then so this is not this may not be a practical case, but suppose you you have the matrix A initially, and then suppose someone already gave a Q, okay, where this subspace of Q is, I mean the subspace spanned by the columns of Q is the same as the subspace spanned by the columns of an A, okay? I mean the column space are the same, okay? So in this case, can we obtain R in more convenient manner? So in this case, so in this QR decomposition form, A and Q are known, okay? So in this case, let's just consider this a Q transpose A and Q transpose QR. Okay, so in this case, I just simply multiplied Q transpose on the left. Okay, in this case, what about this part? Q transpose Q will become identity matrix, and R is Q transpose A. So in this manner, we can conveniently obtain this matrix R. Okay, and also okay, so let's think about it in this manner. So R is, yeah, So we have some Q, maybe having 3 columns, and then each column of an R will have 3-dimensional vectors, right? So we have, for example, 3 vectors in Q, and R will have 3 linear combination coefficient. Okay, and then what does it form? It will form the first column of an A, right? And then the second column of an R, and then that will work as a linear combination coefficient to form the second column, right? And then, so if this vector is already inside of the span of these 3 also normal basis vectors, and then how can we obtain these 3 linear combination coefficient? So if we are given also normal basis vectors, and then U1 transpose Y, and U2 transpose Y, U3 transpose Y. So that was our linear combination coefficient that is associated with U1, U2, and U3, right? Okay, and so how can we obtain this linear combination coefficient? We just multiply, this is Q, and we have Q transpose, where we have U1 transpose, U2 transpose, U3 transpose, and then we have the first column of an A, okay, and then there's a U1 transpose and Y, and U2 transpose Y, U3 transpose Y, okay, so that will become our linear combination coefficient. Likewise, if we have the second column of an A, and then we just put it or concatenate it in a row wise, and then this guy times this, and this guy times this, and so on. So if we multiply Q transpose on the left of an A, and then it will just simply give us the linear combination coefficient when we are given also normal basis vectors. Any questions? Okay, that's it for today. And then also, as I mentioned in the KakaoTalk group chat room, and we will have no class this Wednesday, and then I will ask you to watch some of the online videos that I previously recorded. Okay, thanks.
나랑 행동도 지금 자동차.
온라인 안 돼요. 내일까지. 우리 화요일.
난 한솔이
이렇게 물어봤는데 없다고.